So in the kinetic molecular theory video, we saw that there is a general relationship between the rate of one particle versus another. It's equal to the square root of that second particle's mass, or molar mass, over the first particle's mass, or molar mass. So this rate can describe both speed, but it can also describe the rates of diffusion of particles and also the rates of effusion of particles. This is the equation you'll be using most often with regard to relative speeds of particles. Okay, so we can use this equation to describe diffusion or relative diffusion of different gases. Diffusion is the spreading of gas particles by random motion. We know that particles are continually moving and they collide with each other, and so they collide, but then they can transfer kinetic energy between the particles. But overall, there's a general movement. They collide, they change a little bit of direction, they collide, they change a little bit of direction, they move. This random motion of particles is called Brownian motion. It causes you to have gases spread out. So let's say that you were to put hydrochloric acid solution in one side of a glass tube, a eudiometer tube, and you were to put ammonia solution in another end of that tube. Now these solutions, they're aqueous. However, occasionally you're going to have a vaporization of hydrochloric acid and also of ammonia. Now, where will these hydrochloric acid and ammonia particles be meeting within this tube? Closer to the hydrochloric acid, or closer to the ammonia, or right about in between? Well, we know that we have this rate of one particle versus another can be used to describe the speed of particles, but also diffusion and effusion. You can find that the rate of ammonia versus hydrochloric acid in just spreading out is equal to the square root of the molar mass of hydrochloric acid over the molar mass of ammonia, the square root of 2.13 or 1.46. You see that ammonia travels about 1.5 centimeters, while hydrochloric acid travels about 1 centimeter. Or we can say that ammonia travels about 3 centimeters, while hydrochloric acid travels about 2. In fact, considering that ammonia moves about 3 times, or 1.5 times as fast, or it moves about 3 blocks, while hydrochloric acid moves about 2, we should expect that these two compounds will be meeting closer to the hydrochloric acid. In fact, they'll meet about here. If this were a 1 meter tube, it would be about 0.4 meters from the hydrochloric acid and 0.6 meters from the ammonia. Here at this point you would form ammonium chloride, where you get some solid white compound formed from hydrochloric acid reacting with ammonia. We can also discuss effusion. It follows basically the same mathematical rules as diffusion. Effusion is the escape of gas from a container through small openings. So let's say that you had two balloons, one filled with helium and one filled with neon. Give it a little bit of time. Helium is going to occasionally be colliding with the wall, and even more occasionally going through a small hole in the wall of this balloon. And neon will do the same. But one will do it much more frequently than another. Helium, it travels faster than neon, and hence it will randomly collide with these small holes and go through these small holes more often than neon. Hence, we can expect that this helium balloon will shrink faster than the neon balloon. The rate of effusion of helium is greater than the rate of effusion of neon because helium has a much lower mass and hence a greater speed. In another example, let's say that we had a balloon filled with both nitrogen and oxygen. 1,000 nitrogens and 1,000 oxygens in the same balloon. Give it a little bit of time. What will happen to the ratio of nitrogen to oxygen within that balloon? Well, you see that because nitrogen has a lower mass, it has a mass of 28 grams per mole, whereas oxygen has a mass of 32 grams per mole. Nitrogen will be traveling and effusing faster out of the balloon. How many times faster will it effuse out? Again, because nitrogen is at the top in our rate equation here, where we usually put the lighter one, we're going to use its molar mass at the bottom in this part of the equation. People make frequent mistakes there. And plug in for the molar masses of these compounds, we get that nitrogen effuses 1.07 times as fast as oxygen. And hence, we can expect that 107 nitrogens will leave for every 100 oxygens which will leave the balloon. And hence, over time, we'll see that perhaps you get 893 from those 1,000 nitrogens remaining and 900 oxygens from those 1,000 oxygens remaining. And so the ratio of nitrogen to oxygen will decrease because nitrogen is going down faster than oxygen does. All right, now we also can use effusion for practical purposes. For example, in order to separate uranium-235 from uranium-238, in order to get a high enough proportion of uranium-235 to create fission reactions, when they first made atomic bombs in the World War II, they reacted uraniums with fluorines. They had a slightly lighter particle, uranium-235 hexafluoride versus uranium-238 hexafluoride. And so they could separate these compounds based upon their different masses, and this allowed them to purify that uranium-235 and hence create the atom bomb. Thanks for watching, guys.